Okay, so today we have Hooman Davoudiasl. There we go.
There you go.
From Brookhaven National Lab. He started as a grad student at Caltech. From there he moved to SLAC National Accelerator, where he actually did a lot of the work on the phenomenology of large extra dimensions. So he's a world expert on that. And then from there he moved to the Institute for Advanced Study. He's a postdoc, and then postdoc Wisconsin, where we actually overlapped for a year, but I don't think we interacted.
Unfortunately not. No, I don't think so.
As a student. And then he moved to Brookhaven as a scientist, and recently he's become the group leader of the high-energy theoretical group of Brookhaven. And recently he's also become an APS fellow in 2015, I've been told. So, yeah, let's thank Hooman.
All right, well, thank you, Ian, and thank you all. And special thanks to my host who invited me to come and give today's colloquium. I've had a very pleasant time since arriving here. I got a nice tour thanks to Ian and had many interesting conversations with the faculty. So thanks again. So today I'm going to talk about visible and invisible clues for physics, new physics. And you know, when I was preparing this, I didn't know what exactly one should cover, who is in the audience. So maybe if I can have a show of hands, how many graduate students are in the audience? Oh, good. Any undergraduate students in the audience? Okay. So I just wanted to get a gauge of the audience. Of course, I'll try to go through these ideas, but if at any point something I say is ambiguous or you have questions, please feel free to interrupt. So everyday life is governed by two long-range forces, gravity and electromagnetism. So as you can see, apples fall, and then you can also see the apples, and that's gravity and electromagnetism. So that's basically most of our interactions on an everyday basis are governed by these two interactions. Now the falling apple is the work of gravity, so it pulls the apple down to the ground, and it's for the kinds of everyday experiences we have, Newtonian gravity describes it very well. However, the state of the art in gravitational theory still remains general relativity that was introduced by Albert Einstein more than a century ago now. In Einstein's theory of relativity, which is the state of the art of gravity, space-time is curved by distributions of mass and energy. And for example, the sun would curve space-time in such a way that it would have a curvature. And in this picture, gravitational force, which was a Newtonian concept, is replaced by geodesic. That is to say, when space-time is deformed around the distribution of mass, then particles have to follow a geodesic, which corresponds to the deformation of space, which in this case becomes an orbit. So the notion of gravitational force is secondary to what you would describe as geodesics in space-time. And of course, this description of gravity is the basis of modern cosmology. So if you want to do cosmology at the highest level, this is the theory that describes all the known gravitational interactions so far. And Einstein's equation, which is an innocuous-looking and somewhat misleading in its simplicity because it contains a lot of information, captures this whole idea in the sense that on the left side we have the Einstein tensor, which corresponds to the geometry and curvature of space-time, and on the right side you have energy momentum tensor, which describes the distribution of mass and energy in space-time. And this Gn is what's still left over from this theory, which is Newton's constant. And it, as you can see, it describes both space and time with 4 dimensions, 3 space and 1 time. And in the last year, we had tremendously exciting news from gravitational wave detection measurements, which confirms a long-standing, almost like a century-long prediction of general relativity that's basically says space-time is dynamic, and as distributions of mass and energy move around it, they can emit gravitational waves. And of course, general relativity being tested in so many ways, this was not something that probably was a shock to people who followed gravitational theory. But this was really a direct test of gravitational wave emission, and more than that, it's a manifestation of some really impressive phenomena in nature, which is I'm sure many of you have heard about this merger of black holes. By now, they have two firm events, which correspond to events in September of 15 and December of 2015. In one case, the estimates are two black holes of 29 and 36 solar masses. Those are mass 29 or 30 times the mass of the sun merged. And in the other case, two black holes of 8 and 14 solar masses merged. And both of these events, which are by the standards of the experiments, are now firm evidence for gravitational wave emission, basically were emitted about 1.5 billion light years away. So you have two objects that are tens of solar masses going around each other in a radius of something like 100 kilometers or so, 1.5 billion years back, and they detected this event, which is really an outstanding experimental feat. I really think is one of the most outstanding experimental results, because what they measured on Earth is, which comes from two detectors of advanced LIGO, one in Livingston, Louisiana, the other one in Hanford in Washington, is variations in space-time caused by gravitational waves and the dynamic nature of space-time in general relativity of the order of 10 to the minus 21. And so you have to think about what it takes to measure variations of distance at that level, which was based on very advanced interferometry using lasers. But I don't have the time to really get into the details of that, but I just thought that it deserves a mention in a colloquium. However, the other side of the story of Newton's apple is when they hit the ground. So while it's falling, gravity. But what stopped the apple from falling further? Well, what stopped it was atoms in the apple and the ground interacted through electromagnetic forces largely. So the apple didn't penetrate the Earth anymore and was stopped. So the atoms are made of nucleus, protons and neutrons, and electrons that go around them. And the whole thing is governed by quantum mechanics. And of course, the nuclear forces are of two general types, of weak and strong. And because these are very, very short range and confined to nuclear-sized phenomena, they are not everyday. They are microscopic phenomena. And weak and electromagnetic forces that we talked about before, for some time have been unified into a electroweak theory, which describes both phenomena in a unified fashion. And that has been the status of physics for the past many years, which is summed up in what we call the standard model of particle physics. The standard model of particle physics, as we know it so far, is the most precise description of microscopic physics. And it's based on gauge principles, which is gauge symmetries. You may be familiar with gauge symmetry in electromagnetism, that you have a gauge symmetry degree of freedom. And this idea has been generalized to other gauge groups beyond U1 of electromagnetism, and is described by this gauge group, which is a product group of SU3, which describes in strong interactions, and SU2 and U1. This U1 is not electromagnetism, but it's together with this SU2 describes electroweak theory, which is the unified theory. And these forces act on elementary fermions of spin half, which are quarks that have strong interactions and have charges 2/3 and -1/3. They come in 3 generations: up, down, charm, strange, and top, bottom. And leptons, which do not feel strong interactions but have electric charge or none. And they are neutrinos and electrons. Neutrinos have 0 charge, electrons have -1. And then they also come in 3 families: electron and its neutrino, mu1 and its neutrino, and tau and its neutrino. And all of this gauge interaction gives rise to force carriers, which is our familiar photon, what we call gluon, which carries this strong interaction, and then W and Z that come from this electroweak sector and are the weak nuclear, carry the weak nuclear interaction force. And basically, this is the picture that we knew for sure pre-2012. What happened in 2012, I tell you in a little bit. Strong interactions, which are described by this SU3 interactions, or sometimes called quantum chromodynamics. Chromo because these interactions are called color charges, the charge related to this. They're short range and they're confined to nuclear distances, so they don't go outside of nuclear distances. And what they do, which is of order of 10 to the minus 15 meters, which is a very small size, the strong interactions bind quarks into hadrons. Hadrons are these objects that are made of quarks and bound together by gluons, for example, proton, neutron, and other particles of this nature. And a proton has up, up, down, and a neutron is down, down, up. And because of their electric charges, this has charge positive 1, and this has charge 0, as the name suggests. So that was the the quantum chromodynamics, or strong force. And then there is the electroweak interactions. So electroweak interactions are described by this SU2 times U1. This is usually called SU2 left because it acts on left-handed particles. By left-handed, I mean particles whose spin is anti-aligned to the direction of their motion. So you can think of them as tops, which have direction of spin. And if their spin is anti-aligned with the direction of motion, you call them left-handed. This acts on those particles, and U1 hypercharge. And this whole gauge group is spontaneously broken to electromagnetism, which is manifestations of which we see in our everyday life. Hopefully this is not your everyday life, but it's kind of scary maybe. And so one part of it becomes electromagnetism, which stays as a good long-range interaction. But the other parts become massive W and Z bosons. And the W is 80 GeV roughly, and Z boson is about 91 GeV. And for scale, 1 GeV is about the mass of the proton, roughly. These interactions are short range, as you could imagine from Heisenberg's uncertainty principle. That is to say, you can pop them out of vacuum, and they would only travel a short distance, given energy-time uncertainty relationship. And if you calculate what is the amount of time they can exist if they moved at the speed of light, you get a very small number, like 10 to the minus 18 meters, which is a subnuclear size. So that's why these forces can only be relevant to nuclear microscopic interactions, because they don't travel far. They're not like photons that travel between various large distances. And of course, there is this electromagnetic interaction that remains out of this breaking, which we sometimes call quantum electrodynamics or electromagnetism. And this is mediated by the massless photon. And because this is massless, it can travel large distances and is responsible for many of the phenomena we see around us. So then brings us to what is a spontaneously broken symmetry. Well, let's have a tabletop version of spontaneous broken symmetry. Imagine that you manage through patience and great dexterity to balance a pencil on its tip. If you ever do such a thing, you very soon realize that it's a very unstable situation. And while the pencil standing on its tip has some potential energy stored in it because standing up, it will fall to its ground state as soon as some perturbation happens, and this is not a situation that can be maintained stably, and it falls to its ground state, which is lying on the table. However, the underlying theory, which is the theory of space around it as a fundamental theory, doesn't have any direction attached to it. There is no direction in space as a fundamental notion. It's just that when you stand up a pencil, it has to fall somewhere. And it spontaneously, when it falls, picks a direction on this plane of the table and breaks the symmetry, which was a rotation symmetry going around the table. Before the pencil fell, if it was perfectly perpendicular, you could go around the table, and everywhere you went, it all felt the same, except that when it falls, it breaks that symmetry, and all of a sudden, you see that there is a direction picked here. This is very pictorial and not by any means a rigorous description of spontaneous symmetry breaking in electroweak physics, but it basically tells you what the story is, that the underlying theory may have a symmetry which is spontaneously broken by some field being unstable and going to its ground state. So if electroweak symmetry is spontaneously broken, what breaks it? This is a key question that's been probed at the Large Hadron Collider at Cern. Some of you work on physics of Large Hadron Collider. Some of you are experts on it, so I don't need to belabor. But for those of you who are not familiar with the Large Hadron Collider, it's a proton-proton collider at Cern. It straddles France and Switzerland, and it's operating design beam energies, two beams that each have 7,000 GeV, or in some other words, 7 TeV. Currently, it's running, although it's not running maybe at the moment, but in this run 2, which is on the ongoing, it's running at slightly below this energy of 6,500 GeV. And the whole circumference of this is about 27 kilometers. So it's a fairly large machine that accelerates these protons to these fantastic energies. And because of uncertainty relationship of Heisenberg, as you approach higher and higher energies, you can probe smaller and smaller distances, which would allow you to understand how microscopic physics underlying all of this could work. And then you look for signatures of those things, which is, again, a fascinating and great subject in its own right. Deserves a lot of a whole or many lectures. But today, let's just suffice it to say that this is the machine that currently is probing microscopic physics at the forefront. So I said that this is a question being probed at Large Hadron Collider, but what is the story in the standard model, which, as I said before, is our best, sort of most precise description of nature so far. In the standard model, electroweak symmetry is broken by the Higgs boson, which is a scalar, which means it has no spin. And when it condenses, which is to say a value for this field is turned on. So imagine if you had a capacitor and you turn it on and there is an electric field that is turned on. Somehow this value is turned on in the universe, so this field has a non-trivial background value. That's what this equation means, or inequality. And when it turns on, it endows particles with their fundamental masses. So very often you hear that Higgs is the source of mass in the universe, but the probably more rigorous statement is that the source of fundamental particle masses, as far as we know, the ones that we understand. So it gives masses to W's and Z bosons that I told you before have like 80 or 90 GeV masses, and also gives mass to those fermions, up quarks, down quarks, electron, muon, at least in this theory. And of course, so we sort of understand how these masses come about from the Higgs. However, there is still puzzles related to this mass generation, because the top quark compared to down quark is 100,000 times heavier, which sometimes is called like flavor problem. Why are the fermion masses the way they are? Because they cover a very large range. However, in the minimal standard model, in this minimal description, neutrinos would still remain massless. There is no mechanism to give neutrinos mass within the standard model. However, this is a strongly disfavored situation, because there have been a lot of experiments that seem to strongly suggest that neutrinos have some tiny amount of mass. This plot shows what is called the branching fractions of the Higgs. That is to say, this Higgs, because it couples to all these particles, it can decay into them. So one Higgs can go to two different particles. And depending on its mass, it would go mostly to one type or the other, depending on whether it can go to those particles or not and what's available. However, you can see that if you lie in this region of around 120 or 30 GeV, a lot of branching fractions are available to you. So here you can see that this dominant mode would be going to two bottom quarks, or bottom antibottom, and then tau anti-tau leptons, and then other modes are also available. In particular, an interesting one is 2 photons through quantum mechanical loop processes. But this is an interesting region to be, 120, 30 GeV, because you have all these modes that can, in principle, be probed at the Large Hadron Collider. Oh, by the way, regarding the Higgs and being a source of mass, as I said, it's a source of fundamental particle masses, but most of the visible mass in the universe is actually nothing but the stored energy inside hadrons from QCD. So those gluons that bind quarks inside those particles like protons and neutrons, they store some energy in it, and actually that is most of the mass of the visible universe we see. So on July 4th, 2012, you remember I told you 2012 was an interesting year, a discovery was announced that a new scalar h, which let's call it h, this was discovered at about 125 GeV mass. And this is the early state of affairs when they first discovered this particle. This line 1 corresponds to what you would expect mostly from basically the standard model for these decay branch infractions or decay modes. And as you can see, there was some uncertainty. Some of them were kind of high. Some of them were a little low, but with large uncertainty. And the whole thing maybe was a little high. And between ATLAS, which is one of the big experiments that looks at these things, and CMS, which is another big experiment looking at these things. But 5 years later, which is around now, we have a lot more data. This is from early run 1 data. There was, in some units, 10. Later, they actually analyzed all of run 1 data, which was 25 in units of inverse femtobarn. And the only thing I want you to pay attention to here is that a lot of those things that were moving around this line are now perfectly aligned with what you would expect from the standard model. So in the intervening years, what happened was that this particle that we at the time we called a Higgs of standard model-like behavior or standard model-like Higgs is showing itself to be very close to a standard model-like to a standard model Higgs. However, there are branch infractions of it that are inaccessible to us at this point, and we don't know if you measure those decay modes what you would find. But so far, all the indications that are is pretty close to what you expect from the standard model. So standard model plus general relativity is a great success. It describes, of course, now you can put the Higgs at the center of this story because now you have basically found it. And as I said, there is some great confidence that it's very much standard model-like, even if it turns out at some point to have some deviations. But so far, it really looks like it's close to what you would expect in the standard model. So it's a great success. And now this theory is complete. And particle physics is well described by a standard model. However, one can say nearly all measurements are in agreement with standard model and general relativity because there are some deviations in some experiments. For example, the value of muon's anomalous magnetic moment shows some deviation at the level of 3 or 3.5 standard deviations from the standard model prediction. Of course, this is something that will be soon tested at Fermilab. They're running the old experiment at Brookhaven with a new, so they're using the same setup, but with a new group of experimenters and at Fermilab, trying to repeat this experiment and see what they get. But this is one place that there is some discrepancy. There are also some other anomalies. For example, in B meson decays, there seem to be some anomalies of similar or lesser significance, but these are not at the level what you would expect from a discovery announcement. So that's there. However, regardless of those anomalies and how many great successes the standard model and general relativity have had, one can say with pretty good confidence that the standard model is an incomplete description of nature. And there are two categories of reasons to think that way. One is what I would call theoretical hints, and the other is experimental evidence. So theoretical hints are, for example, why is gravity so weak? Because if you think about it, gravity is a very weak interaction. Or why is the neutron electric dipole moment so small? And it's so small in the sense that if you there is a parameter that you can put in the standard model that if it was a number like 1 or half or something, you would get too much electric dipole moment for the neutron. And the value that is being measured by experiments suggests that this parameter should be less than 10 to the minus 9, which is a very tiny number. So you ask yourself, why would a number so tiny have to be in a fundamental description of nature? But these are just hints that maybe there is something going on we don't understand. But by themselves, they don't point to any new phenomena. It's just that they show that there are mysteries and puzzles that one needs to answer. But there's also experimental evidence, robust experimental evidence that the standard model is incomplete. Two very good ones are the fact that neutrinos have mass, because there are many experiments by now that suggest that neutrinos have some amount of mass, roughly below 1 electron volt or so. And there is dark matter in the universe, which holds galaxies and clusters of galaxies together. And there has been a variety of observations that support that there needs to be dark matter in the universe to be able to describe large-scale phenomena in the cosmos. And so there is really nothing in the standard model that can account for this. So you really need something other than the standard model to account for at least these two things. And there are other hints too from theory side. So let me just go over some of these theoretical hints a little bit. So there's a conceptual mystery. Why is gravity so weak? By that I mean, consider an electron and a proton inside of an atom. If you calculate what is the gravitational force between them and compare it to the electromagnetic force between them, you would get a very small number of order 10 to the minus 40. That's extremely small. And that really shows you that gravity is a very weak interaction. In fact, gravity is the weakest known interaction. I haven't won out, right? Now, you all remember and are familiar with Newton's constant that describes Newton's law of gravitation. And in usual units of NKS, it's given by this number, about 7 times 10 minus 11 meter cubed per kilogram per square second. Maybe this doesn't really tell you why this number is so tiny, because this is in some units that are not too conducive to microscopic thinking. But if you remember that because of Heisenberg's uncertainty principle, you can relate the mass scale or energy scale of something to a length scale, you can actually construct what it would take to have a quantum mechanical description of gravity and what mass scale would it correspond to. For example, you remember that weak interactions corresponded to W and Z mass, which were about 80 or 90, about 100 GeV. But if you construct the Planck mass from Newton's constant, which corresponds to the natural scale of gravitational interactions, you get a number like 10 to the 19 GeV, which is much, much, much larger than mass of weak bosons, and corresponds to a distance scale of 10 to the minus 35 meters, which is very tiny. This basically tells you that you have to get to these mass scales or these length scales before gravity becomes a comparable interaction to other forces of nature. So this is a conceptual mystery. Why is gravity so weak? Or why is this? Or you can turn this question around and ask, why is the mass of the W so much smaller than this scale of gravity? That's the other way of saying what I just said. And this is what points to the hierarchy problem. The hierarchy problem is as follows. We know that the mass of the weak bosons that we have measured and know very well are roughly of order of the Higgs expectation value, or the Higgs mass, because those are somewhat related. They're related. So Higgs expectation value, as we know it, is very close to this weak scale given by weak boson masses. But quantum mechanical phenomena, which I'm depicting with this loop, particles appearing out of vacuum and disappearing into the vacuum, if they talk to Higgs, if they communicate with Higgs, our understanding of field theory, which is the basis of particle physics, suggests that the mass of the Higgs, or the scale of the Higgs, has to be pulled up to whatever this heavy mass is. for the virtual particles that pops in and out of vacuum, and is proportional to its coupling. So naively, you would say if the heaviest particles in nature corresponded to fundamental theory of gravity, which is governed by this Planck mass, and they coupled to Higgs with some reasonable order 1 couplings. 20 minutes? Oh, thanks. You would need a fantastic cancellation between these effects and some other value that corresponds to contribution to Higgs mass to get this very tiny value compared to M Planck. And so the fact that quantum mechanically looks like the mass of the Higgs or the expectation value of the Higgs is unstable against fluctuations to very high masses is a puzzle which is sometimes called the hierarchy problem, which is why there are these very disparate scales in nature. Of course, there's a much more severe case of this, which is the energy density of empty space, which has similar problems, which is a much more severe one, that's a 10 to the minus 120 problem, which is called sometimes cosmological constant problem. And we don't understand that either from underlying dynamics. But the hierarchy problem, of course, has been addressed in various ways. Some have suggested maybe Higgs is composite, like hadrons of QCD, and we don't wonder why those particles are so much lighter than Planck mass, because they're not fundamental degrees of freedom. Once you go into smaller and smaller scales, they disappear from the theory, and something else comes in, which is quarks and gluons. Or you can say there are extra dimensions of strong gravity, which means that you lower the cutoff scale from Planck mass to some lower scales, and then maybe the distance between Higgs mass and that new scale is not too much. And there is also supersymmetry, which many of you have heard about and have probably thought about too, which basically says there are other particles that cancel quantum effects, those loop effects I showed you, and give you the small value of Higgs mass. Of course, if this was the case and this was a perfect symmetry, we would see all these other particles which we don't see. These are the partners of the standard model. And the reason is that, again, this idea is that this supersymmetry is also somehow spontaneously broken, like electroweak symmetry. So and of course, if it was broken at very short distances, then the Higgs couldn't see that symmetry, so it wouldn't be useful. You go back to hierarchy. And if it was broken at very long distances, we would have seen those particles, because they would become macroscopic objects or particles that are within our reach, and we don't see them. So they have to be close to the Higgs mass to be useful. And so far, there is no evidence at LHC for new particles, new physics near Higgs mass, which leads you to believe that maybe these ideas are somehow correct, but they are more elusive than initially thought. That's why we don't find them. Or else this idea of naturalness, on which hierarchy was based, what is a natural value for a parameter, maybe is not the right guide to understanding nature. And I don't want to belabor this point, but you can see that many ideas in the exotic searches of Atlas have been pushed out to beyond 1,000 GeV, which is far from Higgs mass. And even in supersymmetry, these would be the partners of gluons, which are massless, but in supersymmetry, when it's broken, it would be massive. They're also pushed out to TeV and beyond, or thousands of GeV. And the same also for these partners of top, which are important for the naturalness of the Higgs in supersymmetric models. Again, depending on your model and what you're looking at, they are in the 1,000 GeV or more. So all these ideas that were supposed to be close to the Higgs mass, 100 GeV or so, by now have been pushed out. So either these signatures are more elusive than we initially thought, or maybe naturalness and Y numbers should be close to each other by some underlying dynamics was not the right guide to understanding nature. Now let me get to strong empirical evidence for beyond the standard model physics. I told you neutrino flavor oscillation is one reason we really believe neutrinos have mass. And these have been tested in solar, atmospheric, and terrestrial data, which suggests that neutrinos are 1/1,000,000th the mass of the electron, but nonetheless not zero. And there are simple extensions of the standard model that allow you to have neutrino masses, but they are typically difficult to test. Either neutrinos are, you can, for example, add a right-handed neutrino to the standard model and then produce masses for them. But this state is either very massive outside of the reach of colliders or has very negligible couplings to the standard model, which again, you cannot really access. But nonetheless, this is a strong evidence that you need to extend the standard model at least by these right-handed neutrinos and perhaps other interactions. Then there is cosmology. And the very strong piece of evidence there is dark matter, which is a neutral type of substance that fills out the cosmos and is cosmologically stable because it's stuck around for the life of the universe, and that's why we still see its effects. And by the way, dark matter is part of it. Our best understanding of cosmos is that it's 95% of cosmos is made of things that we don't know, 95%. Dark matter is about 27%. Ordinary atoms are only 5%. So most of the matter in the universe is actually dark matter. And 68% of the energy density in the universe is in some form that has negative pressure, is pushing out the expansion of the universe and accelerating it. And they call it dark energy because we don't really know what it is. But it could be vacuum energy, which is that cosmological constant I talked about. Again, its size is somewhat of a mystery, why it's so small in some units. So 95% of the cosmos is unknown. The 5% that we actually know, invisible ordinary matter, we don't know where it comes. We know what it is. It's made of baryons, which is protons and neutrons, and is governed by some asymmetry, which means that there's very negligible amount of anti-protons and anti-neutrons in the universe because we don't see any annihilation signals from nearby astrophysical phenomena, or you can look at the antiproton content of secondaries in cosmic rays, and its content of cosmic rays, and it's consistent with secondaries. But so most of the baryons are of one type. They are baryons and not antibaryons in equal amounts. So there is an asymmetry, and this asymmetry in some units is somewhat small, but it's not clear where it comes from. And the reason is that generation of baryon asymmetry very typically requires satisfaction of what are called Sakharov's conditions for generation of baryons or baryogenesis. You need to have baryon number violation, C and CP violation. This is charge conjugation symmetry, and this is charge conjugation and parity together violation, and departure from equilibrium. All these components exist in the standard model. It's just not at sufficient levels. There are electroweak processes that can cause baryon number violation, and you can use thermal effects to take advantage of this. However, you also need CP violation, which again is in the standard model, but not at sufficient levels. It's too small. And this departure from equilibrium could have come about by a strongly first-order electroweak phase transition, but we know that's not the case, because if that was the case, Higgs would have been Higgs would have been much lighter than what we have observed. So there's strong evidence that it's not first-order phase transition. And so even this 5% that we know, we don't know exactly its origin, and that even also points to some new physics. Now, dark matter, which is the 27% of the energy density, is robust evidence from cosmology and astrophysics, from cosmic microwave background, Big Bang nucleosynthesis, rotation curves of galaxies, lensing, bullet cluster. This picture I showed before, where two clusters of galaxies go through each other, and the dark matter flies through, but the baryonic matter gets stuck, and people can tell that there is some distribution of matter that went through without much interaction, and that's the dark matter. So there is this very sort of almost, you just look at the picture. Of course, you can't see the dark matter, but you can tell its presence by its gravitational effects. But for a variety of reasons, we know there is dark matter in the universe. And its origin is unknown. It has feeble interactions with atoms because we don't see it shine, and doesn't interact much with ordinary atoms. And if it has any self-interactions, they are not strong, but we don't really know if it has any. And one thing that is key here is that there is nothing in the standard model that has the right properties to be dark matter. So it's a strong evidence for new physics. But so far, we only know it through its gravitational effects. So how do you look for something of unknown nature? And to bring to focus the magnitude of the problem, possible dark matter masses can cover more than 90 orders of magnitude, 90 or so orders of magnitude. They can be as light as 10 to the minus 22 eV, all the way to primordial black holes that are several times the mass of the sun. So that's the range we have to contend with. And very often, searches are guided by theoretical motivation. So, for example, you try to solve some other problems, and those other problems can give rise to particles or states that are suitable dark matter, and then that motivates you that if something has more than one use, maybe it's a theoretically motivated idea, and we go look for that. For example, strong CP, which was this idea why neutron electric dipole moments are so small, can be addressed through physics that can give rise to dark matter candidates, or the hierarchy problem, why quantum corrections to Higgs potential are not pulling it away from the weak scale. And when you extend the standard model, very often you introduce new symmetries, and symmetries correspond to charge conservation, as you may know. And of course, charge conservation can give rise to stable or long-lived particles, which can be dark matter candidates. That's one way to sometimes think about this. So far, so good? I guess I have, what, 10 minutes? 10 minutes? OK. So let's look at some of the well-known extensions of the standard model. This strong CP, which I told you, why neutron EDM is so small, it could be addressed by something called Pechequin symmetry, which is a symmetry broken at very high scale, much above W mass. It gives rise to some pseudo-Goldstone boson called the axion, and its mass can be generated by non-perturbative strong interactions. Its coupling is suppressed. However, it could be dark matter if this scale of breaking is about 10 to the 12 GeV, which is very large, which would suggest that its mass is micro eV. Hierarchy problem also gives rise to new weak scale physics, as I argued before. For example, supersymmetry or extra dimensions. And these ideas often require an unbroken parity. For example, you may have heard of R parity in supersymmetry, and if you haven't, it's a parity that is required to avoid problems with the theory. And this can actually make the lightest supersymmetric particle stable, which would then be a good dark matter candidate. As I said, this axion could be a good dark matter candidate. However, you may ask, why is the scale of its symmetry breaking 10 to the 12 GeV? It's not an obvious scale of nature. However, if it was a more, it could be a more motivated scale, like grand unified theory scale, which is about 3 orders of magnitude above this. But that would require some tuning of this initial amplitude of oscillations. And the way axions becomes dark matter is that it basically becomes something that oscillates in the potential, and the stored energy in this oscillating field becomes dark matter. However, how much energy you store in this depends on the initial amplitude of where the oscillation started, how large the amplitude was. And there are axion dark matter searches that use microwave cavity with background B fields, where an axion comes in, interacts with the background B field, and turns it into a photon, which the microwave cavity is tuned to detect. I don't go over too many of these details, just to show that there is activity in this region and people are looking. Then there is weakly interacting massive particles. You may have heard of them as WIMPs. They are set by thermal Rayleigh density. So what it means is that they annihilate in the early universe. And this annihilation goes on until these particles basically can't find each other compared to the expansion rate of the universe. And once that interaction freezes, their density is set. And it turns out that the stronger the annihilation cross-section, the smaller amount of dark matter you're left with, as may be intuitive. And so there's this relation. And this annihilation cross-section goes as some coupling to the 4th over some mass squared, which is typical of these dark matter particles. And it turns out that if this mass is of order TeV, you get roughly the right amount of dark matter. And this TeV, as I said, was theoretically motivated by hierarchy solutions. So This is something sometimes called the Wimp Miracle. However, this ratio could also be achieved in other ways, which would give you the Wimpless miracle if this G and M are chosen suitably, even if they're not, this mass is not around TeV. But this motivates people to think about this possibility, and it has been a focus of many searches over the years. There is direct Wimp dark matter searches where they look for the recoil of these dark matter particles off, say, nuclei or electrons by the standard model, in the standard model. And they look for energy deposition by dark matter into the target material, which is, ordinary atoms. There is also the notion that as the solar system moves within the galaxy, if you think about it, there is a dark matter wind that we face, and this dark matter wind is modulated by the motion of the Earth around the Sun, which is sometimes aligned and sometimes anti-aligned with this wind, and that can cause modulation in this detection. I don't go into that either, but it's just a possibility that some experiments have looked into. As far as I can tell, there is no robust evidence for dark matter in these detections. And the chair of the talk tells me I only have 5 minutes. I thought I had a little... 10 minutes, is that right? Okay, sorry. So 10 is correct? All right, thanks. Sorry. But the point is that so far what we have are bounds. And there is no irrefutable signal for dark matter from these experiments yet. I don't go into this. It's just that you can see that a lot of these searches are sensitive to tens of GeV to hundreds of GeV dark matter masses. And as you go to small masses, there is the interaction cross-section with nucleons here is poorly constrained because the recoil becomes inefficient. So as you go towards light masses, let's say few GeV or less. There are other ways of looking for WIMP particles through indirect searches of their self-annihilation signals. So I told you that they can annihilate in the early universe to set the right relic density. But that process can still go on at some small level, even today in the universe. And so you would expect at some level to see signals of dark matter annihilating against each other and giving rise to signals in visible matter. For example, Fermi telescope has been looking for those. Again, so far I don't think there is any signal that is robust. And you can also think about producing dark matter at colliders like Large Hadron Collider by smashing standard model particles together and turning them into dark matter, which would then show up as missing energy in your events, because these dark matter particles leave and take energy with them. But again, so far doesn't seem to be any clues from experiments. However, dark matter could be actually from a dark sector, which means that it could be from a sector that has its own forces and particles, kind of like the standard model. We know that the standard model has multiple components, has various fermions that have various forces, feel various forces, and maybe dark matter is like that too. And there has been a simple example in recent years. For example, you can assume that dark matter is from a sector that has a U1, kind of like electromagnetism, but dark electromagnetism. And it's mediated by some particle ZD of some mass mZd and coupling GD. And it somehow interacts with the standard model through what I call a portal here, which means somehow by mixing. I don't want to get into the details of this too much. And for various reasons, this dark photon, which is not like photon, which is completely massless as far as we know, this one is postulated to have some mass, which is usually at the order of GeV or less. So, and again, GeV roughly is the mass of a proton for scale, although it has nothing to do with the mass of the proton. This has been invoked in the interpretation of certain astrophysical data in terms of dark matter, or even explain this G-2 of mu1 that I told you was had some discrepancy from its standard model prediction. And you can imagine that the mu1 can exchange with itself, basically, a dark photon, which would contribute to this anomalous magnetic moment. I don't get into the details too much, except that this U1 can mix with the U1 hypercharge of the standard model by small parameter epsilon, which would then cause it to couple to electromagnetic currents, just like the photon with a strength E, but suppressed by this small number epsilon. So that's why we call it dark photon, because it's not as strongly coupling to electric charge as photons, but by very small amount suppressed. And that's how, for example, you can imagine that it couples to muons, because muons have charge -1. And this mixing can actually be induced by loop processes, where a photon couples to some particle that has both electric charge or hypercharge and this dark charge. And then this causes photons and this dark photon to mix, which is then represented by this Lagrangian. I don't want to get into too much details of all these experiments. I've been looking for it. There has been an active experimental program to search for dark photons. An early target has been G-2, where this band is where you would, in the plane of mass of dark photon versus this epsilon squared coupling, you could explain the G-2. But the point is that if these dark photons decay visibly, this has been ruled out, more or less. And even if they decay invisibly, so imagine that the dark sector has some light particles that the dark photon can decay into. Because these particles are in its own sector, it's very likely that it couples to them very strongly, which means that it would almost always want to decay into these things and becomes invisible, because these particles are also in the dark sector. And even then, your constraints would be different, but there have been, for example, Babar has ruled out this possibility as an explanation of G-2 as well. So the simple versions of the dark photon explanation are gone. However, this invisible dark photon gives provides an interesting possibility, which is production of dark matter beams, because then you can imagine that you can, for example, slam a beam of electrons into a target and produce these dark photons through these tiny interactions it has. And because these are light, they come out with a large boost and decay in a collimated fashion into dark matter. And of course, other particles get stopped by some shield, but these dark matter particles continue. And because of their dark photon interactions, they interact with the detector downstream of the target. And you can actually then imagine producing and detecting dark matter in the lab with these type of experiments, which is nice because these are usually useful for light dark matter, which was a challenge, if you remember, for the direct detection experiments because of low recoil energies. Again, there are proposed experiments and already some also results using this technique, which I don't get into, but some future and some existing data. And this is, for example, Mini-Boon, which is an experiment at Fermilab. They used a proton beam dump to search for dark matter in this mode, and they already have some constraints, as you can see, with the solid lines, assuming quark nucleon couplings, and these dot dash lines are from other considerations that also assume electron coupling. And for this particular exercise, they assumed that dark matter was light compared to dark photon, but was a scalar, not a fermion. If I have 2 minutes, then I cover this, hopefully. It's 2 minutes, okay, 3 minutes. So far I told you there were some theoretical motivations that actually motivate you to look for some types of dark matter, for example, hierarchy or solving the strong CP problem, why the neutron EDM is so small. Observations can also give you some hints on what dark matter could be. For example, here's one observation. The amount of dark matter in the universe is about 5 times the amount of baryons in the universe. So you remember it was 27% compared to 5%. And these are two types of matter that, as far as we can tell, have nothing to do with each other. They have very, very different properties. But so you can ask the question, why are their energy densities so close to each other? Factors of 5, not 50 or 5,000. And one idea is that maybe dark matter, like the baryons, is set by an asymmetry. And maybe baryons and dark matter come from some underlying common origin which gave them asymmetries. Of course, then, if these asymmetries are of similar magnitude, then you have to explain why dark matter is about 5 times heavier than protons. But that basically changes the sort of type of energy scales and mass scales you look at. For example, instead of looking for hundreds of GeV, you start looking for several GeV. But then you may have ideas for how to explain why dark matter should be only a few times heavier than baryons. So one idea of this type that we considered some years ago with my colleagues, we called it hylogenesis, which was genesis of matter. Ili in Greek, I understand, means matter, so we chose this name for it. And so what we assumed was that dark matter and baryons have a generalized global baryon number, and there is a out of equilibrium CP violating decays of some particle that give rise to an asymmetry in quarks and dark matter at the same time, but of equal and opposite value. Dark matter came out, again, as I said before, of few GeV, and it had 2 components, a fermion and a scalar. You could make the matter and dark matter stable by some assumptions, but the interesting part was that because of the structure of the theory, baryons and antibaryons, which are dark matter in this case, can annihilate each other. And we call this induced nucleon decay. It is really a scattering process. So you can imagine that you have a baryon sitting there, and a dark matter particle comes in, and you can actually annihilate it and give you an anti-dark matter particle, which then carries the baryon number with it. There's no baryon number violation. It's just that you put it from one place to the other, and a meson. So from an outside observer, it looks like a nucleon, like a proton and neutron, disappears and turns into missing energy, which is this anti-dark matter that goes away, and a meson that comes out. So you see the meson. So it really looks like a nucleon decay, but it's actually an underlying scattering process. And the interesting thing that we found was that, first let me tell you that even though it looks like a nucleon decay, effectively it has different kinematics, because these particles, this is a 1 GeV type particle, and these a couple of GeV particles, and the momentum of the meson that comes out, if it's a decay, a standard decay, because it's a 2-body decay problem, it's completely fixed kinematics, you can actually calculate what's the momentum of the meson for any meson that you consider. However, here, depending on the mass of if it's a lighter dark matter going into a heavier or heavier going to lighter, you can actually get a range which is much harder in terms of momentum than the meson. So at least in a nucleon decay experiment, these would be much harder mesons than you would expect from standard decay. And the one thing that we found was kind of intriguing was if the scale of these particles that generate the asymmetry and the underlying scale of the problem is given by this TeV, which was somehow motivated maybe by some hierarchy sort of consideration, the effective lifetime of a baryon sitting in our neighborhood of the galaxy, which has this particular dark matter density, would come out to be 10 to the 32 years, which is not far from where experiments search for nucleon decay lifetimes. So it actually is interesting that you can, because of the proximity of these numbers, you may actually use nucleon decay experiments to look for these and take advantage of these different kinematics, which would make it possible that even if this has happened, may not have been captured because the kinematics is different enough that could lead to signals that have escaped the experimental selection criteria. Anyway, I don't want to go over my time too much, so let me just conclude here. The standard model and general relativity successfully describe a wide variety of phenomena in nature. And of course, the standard model needed to be completed by a Higgs boson, which appears that the particle that was discovered by LHC conforms to and completes the standard model. However, we don't have a no-lose theorem, because before the discovery of the Higgs, the idea was that if you reach energies of order 1 TeV, 1,000 GeV, you either find the Higgs or something that has to do its job for you. And so you had the notion that we will discover something, either the Higgs or something else. That was sometimes called a no-lose theorem. Well, we have found the Higgs looks like. So, and I'm not aware of any other no-lose theorem for experiments that are accessible to us that would necessarily find anything. But there are these arguments based on hierarchy or naturalness that still give some motivation to go and look in this region. But we are at an interesting time in particle physics. Standard model has conceptual difficulties like hierarchy or strong CP, and these can be addressed with some new physics, but there is no firm evidence for any of the associated physics to that address these conceptual problems. And it may be too early to talk about this, but if naturalness and hierarchy and things like that are not a good guide for what's next to be discovered, perhaps we need a new organizing principle for what's the right way to think about new physics. But there are, regardless of these theoretical hints, there are empirical shortcomings of the standard model, like neutrino masses, dark matter, and even baryogenesis, as I described, which require new physics. There is a wide range of possibilities, for example, for dark matter. As I told you, Wimp dark matter is motivated by naturalness, which is under strain. There could be observational clues that guide you to do different kind of model building, for example, asymmetric dark matter. And I gave you this particular realization, halogenesis, that we had that gave rise to this Nucleon annihilation with dark matter, which could principally be searched for in Nucleon decay experiments. But we'll see if anything turns up, if the scale is near TeV. Anyway, thank you very much for your attention.
Thank you very much. So we have time for one question, if there is any further question. Yeah.
There is another fix for many of the problems, at least some of the problems. It's just as wrong as probably most of the things that you talked about here, but if general relativity is not the thing that tells us about space-time or about gravity, then we don't need dark matter at all.
That's I presume you're alluding to Mond theories, modified Newtonian dynamics, if I say it correctly. That's one, or that is something that various people are investigating. I'm not an expert on that. It seems like sometimes those models can describe what you would ascribe to dark matter on one cosmological scale, but not on multiple cosmological scales, which, as you know, is the problem of dark matter. It seems to be present around galaxies, in clusters of galaxies on larger scales. So I don't know how far those theories can go and universally describe everything, but it's true that, so to that extent, there may be something there, but it doesn't seem to be as successful as the simple addition of a new degree of freedom, or new state, dark matter. Although we don't know what dark matter is, could be multiple things, may not be one thing. So.
Thank you very much. Thank you.